Hi everyone. Welcome to the lab session 3 and I hope that you've understood the previous two lab sessions. I've got a lot of mails from people appreciating and that they're understanding. So it's a good thing. So let's begin with today's lab session about and it's about control flow in ALP. So last lab session we saw that how to bring data from your assembly language program to your debug X and store it in particular memory locations. And one thing very important which we learned was that ALP is for us to write, but bytecode is for the machine to understand, right? But for our understanding purpose, sometimes we have to go and check those memory locations where the data is stored. Therefore, it's important for us to know as well where our data is going, where the instructions are loaded, etc. All right. So with that, let's uh, keep the discussion going. Compare instruction. All right. So like in C code, we've C code or Python code, we all have used control flows, right? The if else statements, the for loops, the while loops. Now, we simply use if else statement, but what is happening, what microprocessor understands are these instructions. So all these if else statements, all these for loops and all these comparisons are actually, a subset of the compare instruction and the jump instruction put together. So let's dive right into it and let's try to understand this. Okay, so the compare instruction and let me take out the pen. All right. So the compare instruction is a subtraction that changes only the flag bits. All right. So this is one thing very important, that it is same as subtraction, but it's not going to store the result again. Subtraction, I think sir might have already taught you in the lab session, in the lecture series. In our next lab, we'll be discussing about the mathematical operations in ALPs. But as of now, it's just going to affect only the flag bits. So the format of the instruction is compare destination and source. So here you can put a register and here you can put a memory location. So this is memory, this is register. Here there is a register and an immediate value is there. All right. And here again the destination is a memory location. This complete thing is a memory and this is a register. So but there is no such thing as comparing two memory locations. You have to, you know, just avoid those sorts of that you can do by bringing in some data, but that you don't directly do comparison between two memory locations, just like our move instruction. So let's look at an example that how the bits are going to be affected. All right. So if I do compare cx comma bx, then there are three scenarios. All right. Either cx is going to be equal to bx, either it is going to be greater than or less than. All right. There is no fourth thing possible. So in each of these scenarios, how the bits are being affected is shown here. So definitely, if both of them are equal, zero flag is going to be one. If cx is less than bx, then there would have been a borrow, obviously, because it's cx minus bx, right? Therefore, carry flag is set to one, and also the sign flag will also be set to one because it would result in a negative value. And if cx is greater than bx, then all these, like, definitely this does not matter here, but carry flag and sign flag both will be zero. All right. So to check the results of compare, actually, just remove the logical here. There are two possibilities, that either we do a logical comparison or we do an arithmetic comparison. Okay, so if you're doing an unsigned, uh, like as we progress, you'll get more clarity when we go for signed, when we go for unsigned. Simply put, if you're doing any arithmetic operation, because all the arithmetic operation happens in two's complementary form, therefore you're that time you're obviously going to do the signed comparison. Okay, so if you're doing the comparison logical, then after doing the comparison, you have to take a decision, like why have you compared this, so that you take a decision, and that decision basically boils down to a jump statement. So simply put, that if let's say, if you know if you want to write cx is greater than bx, then do something like in your c code. If you want to write this, then this would translate to actually, first you do this comparison here. So you do something like compare cx comma bx, and then based on, like, what this sign is here, this greater than sign, this you try to encode in some jump statement. So it can either be jump, so if this is a logical comparison, then jump above, jump below, jump equal to, jump not equal to. Like, broadly, these four things we generally use: above, equal to, and all those things you can also mix and match. But these are the this is primarily what you have to think through. And if you understand this concept clearly, then I think rest all of the lab sessions, all of your mid-sems compres is going to be a cakewalk. So only thing which you have to focus on is how to convert this if else into a comparison and a jump. Okay, so with that said, so if the uh, I'll just quickly point out, when we are using all these things. So jump above, all right. So jump above means that cx is logically greater than, I won't again and again say logically, but just understand that cx is greater than bx, all right. Jump equal to, so let's discuss these two because these are the most common scenarios which we obtain. So if the zero flag is equal to 1, that means they both are equal. You don't always have to think this in your mind, just you can simply say that if, if you want to write if cx is equal to bx, huh? So that is the time when you go for, if you want to do something inside the bracket, right? So it's actually reverse. Once you start doing the questions, you'll see that what code goes inside the bracket in your typical C language will be some that will go outside here. All right, we'll get to that. And here zero flag would be equal to 0. Okay, so jump equal to, so if there is a JE statement you have written here and you write somewhere, let's say a location x2, then if both of them are equal, it will jump outside. Basically, it will skip all these codes which is written here. So that's what I was trying to say, that uh, it will, you slightly have to change your algorithm, but point is that both ways it will work. It's not a very complicated thing, but you want to skip these things. So if this was not equal to, then all that code which would have gone come here would be, you will be writing it directly here. Okay, I hope this is clear. All right. So similarly, there are other other comparisons also. I'll quickly write them down. You can pause the video and think through this, but most of them are very straightforward. So if carry flag is equal to 0, carry flag equal to 1, carry flag equal to 1, or 0 flag equal to 1, and here it will be carry flag equal to 0 and 0 flag equal to 0. Okay, so if cx is greater than, as we had seen in the last slide, if cx is greater than bx, then carry flag and 0 flag both will be 0. If it is below or equal to, then it will be carry flag equal to 1 or 0 flag equal to 1, either of these things. And if it is below, obviously carry flag 1. If it is above or equal to, then carry flag equal to 0. Just think through this, and there might be some modifications also based on this. This is just very straightforward approach. All right, so next, like, let's quickly do it for the arithmetic as well, because in arithmetic things will be slightly changed. Let me rub this thing here. Okay, let me change the color as well. Let's try this color. So obviously these two things are very straightforward. Again, oops, this color is not that visible, right? Let's go for blue. So if zero flag is equal to 1, same as the logical operation. But in arithmetic operations, it's not just the carry flag which is important, all right? It's the XOR of sign flag and the overflow flag. So in all of this, just you have to check this thing, and this microprocessor will do for you. You don't have to do it. You just have to write this instruction in your ALP, and microprocessor will do it for you. Like, that's obvious. So if it is 0 here, 0 1 1, or 0 flag is equal to 1, and here, and 0 flag is equal to 0. All right. So if these two bits are true, then that definitely means Cx is greater than, which also means it is not less than or equal to. So in your ALP, you just have to quickly identify and fill this information. All right. So let's do a follow along example, everyone. By the way, this is a good news for you people that I have started to maintain a um, repository. Please go ahead and also click on watch. Also start this repository. Okay, don't forget to do that. And I'll keep on whatever codes we write in this lab session, and you'll find them in the week 3. So you just have to appropriately, you have to go to that weeks branch and you'll see all the code written there. All right. So let's open the DOS box. I was actually trying few things out before, before taking this lab. So I've already have most of the code written, but still I'll write in front of you. All right. Okay. So let's go over through the first follow along example, which is write an ALP to copy 10 bytes of data from memory location pointed by source data to memory location destination data. Here, like this is just you can think of this as data. All right, or you can say here whatever is comfortable for you. So here I have DB, which means that if my memory is here, then at each and every memory location, this value is, since it's only 1 byte I'm giving, so I don't have to put it as 0003. Okay, so 06 AB 07 08 09 10 11 12, and all of this is in hex format. So whatever this, if I do a load effective address and in the bx register I store source data, then basically what the bx will contain is the memory address of this first location. All right. And what I have to do is I have to copy 10 bytes of data from this source data to another memory location, which I have pointed by destination data. Okay. So ideally, what if I store it this in SI and I store this in DI, the destination data, I have to copy this. And obviously there is no such thing as move memory location to another memory location. So I might, like very naive approach. So just pause the video, give it a try, and we'll look at the solution. Okay. So let's look at the naive algorithm. And since mem is not possible, therefore, let's actually type this, and so that because you might seen the code written many places, but not everywhere you can. So let me create a new file and copy this basic thing for you. All right, so everyone should be very quick whenever you get this sort of a problem. You should be very quick in typing at least this basic part and just write dot exit, and end. So don't wait for writing the entire program and then compiling it and seeing what is happening. Just if you have written some basic code, just see whether things are working for you. In the end, like if you write a very complicated code and it throws an error, you don't even know where to start debugging, because the errors are not very clearly defined here. What is the error? All right, so as a good practice, what we had learned. Let me leave one less space. Yes. So if I store LEA and in SI, I want to store the source address, the pointer to the source. I'll keep things standard. Uh, okay, source data, then load effective address, destination index. All right. Now what we have to do is, first step is how many bytes we want to move. So that count I'll store it. So this is like, there's a more efficient way of doing that. I'm going ahead with the simple explanation. So 0 in CX, I'll move. What value should I move? 10. But since I have told in my tutorials also, and I've clarified this many times, that it's always easier to just deal with hex in here. So instead of writing 10 as a decimal, I would like to for my clarity only, store it as 0 so that I'm just aware of what is happening. I just want to keep things in hex. My life is very simple in that way. So that I'll move this count to CX, and then just I'll empty the AX register so that I can move my data and there is no confusion. There is no need to do that, but since we're doing it byte by byte, that means 8 bits, 8 bits, and each of these registers has a capacity of 2 bytes. Therefore, I just have to use the lower part of it. All right. So now comes an important concept of memory location. So I'll mark this point of my code as x1, and what I'll do is, first thing I'll in the AL part, so I'll just copy 8 bits from SI into my AL register. All right, clear, no big deal, correct? Next, what I would like to do is move whatever is there in my AL register to the memory location DI. Okay, and as of now, let me just compile this and see whether it is working or not before Uh, so I'll name it as example1.asm. Exa1.asm. Okay, so ml exa1.asm. So it is compiling. That's a good sign. And debug x exa1.com. Right. So let me see. So definitely, as I've told you, that it's always good to just mention the source is at location 0016. Basically, this is the memory, and the destination is at 0120. All right. So let's examine those memory registers, and let's try to execute up till this point. So DDS 0116. Oops, DDS 0116. All right. So I can see that it is exactly matching up 030506 AB up till 12. All right. And after that, there are 10 locations which are completely empty for me to put in the copy data here. Okay, so let me see, like as of now, only the 03 must be coming if I run the code up till this point, 0112. Okay, so let me run the code G till 0112. Always, wherever move AH comma 4C is there, you can directly execute up till that point. So 0 1 1 2. Now let's examine the same memory location in DS. 0 1 1 6. Okay, so I see that 3 has come here. That's a good sign. Now I need to copy the other things as well. All right. For that, like I have to move my SI, move my DI, and then uh, do some comparisons also, because I want to decrement my CX every time I do this operation. I have to decrement my CX as well. All right. So the next step here would be to increment SI, increment DI, and decrement the count in the register CX. All right. And then just compare whether CX has become 0 or not. So compare CX with immediate value 00H. It is not equal to, then I need to shift back to X1. So if it is not equal to 0, then I need to shift back to X1. Clear? So Control S, quit ML debug X, just seeing the memory location. So here you can see, like, it's a very good thing, like if you try to do the trace command, and you can exactly see, like here, and things get more interesting when you actually start seeing, okay, the next instruction actually has been skipped. And in the next follow along example, we'll see that. As of now, we can directly run G 0 1 1 A, and just to make sure that we see the correct memory location, I'll note it down. So source, oops. So source and destination. Source is given by 011E and destination is 0128. Okay, 011E. So let's go and first of all check 011E. Okay, I can see all the elements coming here, and after that 10 memory locations are empty. Okay, and I want that all these things should be repeated here. So let me execute my command up till the point 011A. 011A. All right, now let's again check the memory locations. DS 011E. Okay, nice. 0303 up till 10, 11, and 12. So the code has worked. So this is one of the naive ways, like, nothing interesting, like we've just done it as a simple method. But there is an interesting method to this as well. And let's get to that. Let's use a new instruction to do this. Now, since it's right there on the screen, I won't be typing it because it unnecessarily wastes time. So the new instruction is move SB. Try doing that. Try doing that, and you'll find very interesting thing that it's sort of memory to memory transfer. So you don't have to store it in AX or here and there, do all these. It will automatically even increment SIDI and decrement CX automatically. So all these operations which you wanted to do, so it will do it for you. Just you have to use move SB. All right, do give it a try, and let me know how it goes. There's an important keyword here as well, rep. All right. So using these commands will decrease the size of your ALP and will make things much more simpler for you to understand. So these small techniques, if you just keep on utilizing this, no one is telling you or forcing you to use this command, but it will just be very helpful for you. Like all these complicated things, incrementing that. So if you know that, if you anytime you have to copy this data, so you can just use move SB. Similar to there is store and load SBs, like load SB, store SB. We'll come to that very soon. So we have another follow along example, and take your time, pause the video, write an ELP to find the greatest signed number from a set of 10 bytes stored at location array 1 and store the greatest number at location result. All right, pause the video, do give it a try. All right, so let's discuss the solution. And as you know that I've already written this, so let me open it in VS Code and show you this thing. I would have loved to type it again, but I think it's straightforward. So let me just explain you from here itself. Okay. Let's change the color to red again. Pinkish. All right. So why do I want to know the effective address of results? Just so that, when the instructor comes to check my uh, coding, whatever I have done, I can just show him like this is the value where my result is, because he will not be knowing, because 100 people are running, there might be for everyone different memory locations are there. But how will the instructor know that which memory location to go and check? So therefore it is important that you somehow note it, that you show it first, and for you to know that, you have to best ways to just load it in some register and check the value of that register. All right, so have you understood the question first of all, that we'll have some register bx, and we'll keep on taking it to different thing, like different arrays, incrementing it and making a comparison. And if we find all this is, it is given signed, right? So if it is, let's say, 9 1h, so 9 1h will basically become a negative number because we're doing the sign 2's complementary representation. All right, so only difference would be like this GE, this jump statement will make a difference for you. Okay, so how many operations, how many elements are there in the array? Z 0a, so that I'll store it in the CL register. And and lastly, in the last step, what I'll do is, like if I was writing the code, I would have first done this part and compiled it before running the whole thing. Like I would have in the result, whatever the result is, uh, in that place. In fact, just a second. All right, fine, perfect, nothing wrong. So in that result, whatever this memory location is, I'll put the contents of AL register. And what I'll be storing in the AL register is the largest number from this. So it's very simple and straightforward to follow this. So let me type it only so that none of you are, feeling sir ने explain नहीं किया सही से. Let me delete up till this part. Okay, because यहाँ से main logic start हो रहा है. From here the main logic is starting. So up till this point, I'm storing 0a, and I'm storing the first element. I'm assuming that this will be the largest one. So it's a normal CC code here, it's not very complicated thing. And that I'm storing in the AL. After that I'm decrementing the count. So I can as well have skipped this statement, and you would say, sir, here I can do that. All this is very obvious, so just it's up to you. Okay, it's very obvious, you can do that. I'm just doing it for the sake of clarity. And then you increment the bx register. Now the bx register is pointing to this 02h. Okay, so the first thing is I want to make a comparison, right? So let me do the comparison operation. So compare, and what do I want to compare? I want to compare whatever is the content of my AL register, and the memory, which is the address is pointed by the contents of the BX register. Simple. Next, if if the content, so in the question, see what I have asked. In the question, I have asked greatest signed number. Okay. So now, if the comparison, if AL is greater than or equal to, okay, if AL is greater than or equal to whatever the contents of the memory location BX, then I would skip the next line of code. I would skip the next line of code, which I'll come to back later, and I'll start executing from this point onward. Skip. All right. And in skip, I'll just continue with my operation. So think of it in this way, like you have to understand that how am I thinking while typing. Seeing a code and understanding is easy, but once you're actually typing it, this is how you have to think. Okay, I have to increment or something, do something. But if it is not greater than or equal to, what do I have to do? I simply have to move the contents of BX into AL. Straightforward, right? I'll after that I'll increment my BX. I'll decrement the value of CL register, and I'll do comparison like whether CL is read 0 or not. So if not 0, jump if not 0, back to which memory location? X2. So keep on doing this as long as CX is not 0. That's what it basically means. And after you have completed this loop, you've done everything, just simply, as we discussed in the starting, do a move operation, and in the result, store AL. Okay, let's save this. So basically, if I do a dry run on this, initially 91 will be stored. Initially 91 will be stored in the result. Sorry, in AL, actually, I'm talking about the contents of AL. Initially 91 will be there. After this first comparison, 02 will be there. Then 83 is a negative number, FF is a negative number. Like these comparisons will not take place. Then for 75, this again, this line will get executed for 75. Then it will remain this way because 06 is smaller, 47 is smaller, 12 is smaller, and then finally for 76 this will happen. This line will get again executed. So I would highly encourage you to try the trace and do that. I will do the trace up till certain point, and then I will simply use the uh, G command to execute the complete thing. Okay, so let's save this and head over to the DOS box. Let's compile this as ex2.asm. Compiled, not a problem, not an issue. But not a very good habit to compile, once you've written the complete code. I would highly recommend that you keep on compiling it time and again. Just verifying, micro steps, small steps, so that it keeps on giving confidence that at least you're getting somewhere. Like, it's not like a complete absurd thing for you. So debug x example 2 dot com. All right. So 012b 0122. Let's note this down somewhere. Result will be available at location 012b, and the array one's first base pointer is 0122. So let's go to this and see. Let's go to DDS 0122. 2 2. So I can see my um, array fully loaded into this. Cool, up till 76, right? And next, what I want to do is keep on doing the trace command up till a certain point of time where you can start understanding things. So the first thing is load effective address, the B of result. That is just, note down the value, not a very important thing. So trace going on, continuing, moving the count 0A. So you can see right here that 0A is has come here. All right. After the execution, CX has become 0A. So again, next would be the contents of the AL will change. So here in the AL part, 91 has come. It's a good habit actually to clear, first do move AX 00 just to, make things very clear. But as of now, we're just concerned with AL. So ignore this FF on top. Now you want to decrement the CL counter by 1. So that has got decremented. A minus 1 is equal to 9. Done. Increment the BX so that it's pointing to the next memory location. Do a comparison. So AL and the data at the BX location are compared. And next thing is, if it is greater than equal to, then skip. Will that get skipped? No, it will not get skipped. Because we already know that it will execute this line. All right. So AL comma BX. So now in AL 02 is stored because that is bigger than 91. Let's do it quickly now. Again, this comparison option is there, and we have reached back to the point, this point. Will this get skipped now or not? You don't have that operation anymore. So you know it's working basically. The microprocessor works, the simulator works, everything works. And if you're not able to get it worked, it's basically because you have written a wrong ALP. So now I'll simply do one thing. I'll execute up till the point 011D. So G011D. Okay, now the time to check whether my result memory has this or not, because I can see in AX there is 76, which is the last thing. Definitely a good sign. And the memory result is given by DS. I'll just type 0122. All right, so this is 012B and it has a 76 here. So the code works. And all right, I hope that this video has given you a lot of clarity. So these are your lab tasks. Task 1, write an ALP that will examine the contents of set of 10 bytes starting from location array 1 for the presence of a particular data and replace it with ASCII character E. Okay. So store ASCII character also in the data initially, like store that also, like it's the ASCII value of E, but you can directly put it there. But a better way to do it is give it as a variable here, as a data here in your data. Task 2 is write an ELP that will count the number of negative numbers in an array of 16-bit signed data stored from location array 1. All right. The number of elements in array 1 is present in location count, and the count of negative numbers must be stored in location neg1. So I've not filled this array for you. You can take it 5, 10, 15, how many elements you want, just do that, make and fill it with an appropriate count. And now using these two as variables, write an ALP, generic ALP, all right? And whatever the result is, store that back in egg1. Okay, so that is it for the video, guys. And if there is any confusion, let me know. And do give a feedback. I love reading your mails. So thank you so much.